Welcome to EPG Pathshala program in Linguistics. We are going to discuss a module from the course Introduction to Computational Linguistics and Speech Processing. The coordinator of this course are Professor Pramod Pandey, JNU, and Professor Deepti Misra Sharma from IIIT Hyderabad. The title of this module is Database Preparation and Labeling for TTS System. The author of this module is Professor Hemant Patil from IIT Gandhinagar. I am Amardeep Kumar Singh, School of Computer and System Sciences, JNU. I am presenting on behalf of Professor Patil. Outline of this module. In this module, we are going to discuss the methods of text collection, the steps of collecting the database, then recording of speech data, then labeling of speech data at appropriate speech sound unit level. The labeling of speech sound level will be discussed for two methods. The first one is phoneme-based labeling and the second one is syllable-based labeling. The database collection is a vital component in any TTS system. Its preparation includes collection of text for recording purpose. Thereafter, the collected text is recorded from a native speaker who has good command over the language. There are various research studies about the process of data collection, as will be described in the following subsections. This data preparation may vary with the language for which the TTS needs to be built and the availability of resources for that language. The conventional procedure for data collection includes collecting large amounts of phonetically balanced text that can be used to record speech in highly controlled recording studio environments. Well, in the following sections, we will study about the several steps of such a database collection. The first one is text collection. So, the text selection for any TTS system depends on the domain or specific application for which the TTS system is being built. For example, the text can be collected in following two ways: domain specific and open domain. In domain specific system, the recording is done of domain specific prompts which must not only cover the most frequent words in the domain. However, they must also provide a good coverage of the prosodic context in which they appear. While in open domain application, the common words, the corpora, can be collected for different major domains like sports and games, finance, news, culture, magazine, articles, stories, essays, consumer information and personal communications, etc. Collected as much as possible in the form of sentences. The text will include foreign words, numbers, designations, abbreviations and other non-standard words. Once the data that is collected, there are many other cases of very common words that are not covered in such a corpus. However, they may be useful. This may include numbers, financial terms, currencies, names of the countries, and their capitals. It is also possible to manually create such sentences to provide coverage for these items. The amount of data to be collected depends on the type of TTS to be built. For example, in unit selection based TTS system, the huge data corresponding to 10 to 15 hours of speech data needs to be collected. While this may not be the case with statistical speech synthesis techniques, which requires 2-3 hours of speech data to build TTS voice of acceptable quality. After collection of sufficient text data, a common procedure will be cleaning and processing of text where symbols like numbers and abbreviations, etc. needs to be converted into the equivalent of written out words. The second step is text processing. This is a pre-processing step where unwanted text may be removed and numbers, abbreviations, acronyms, etc. are transformed into full text. So, there are two steps in this processing. The first one is text cleaning and the second one is text normalization. The collected text from electronically available text from web resources may contain various HTML tags, markup, etc., which are not language dependent, and also they may not be synthesized. For example, use of emoticons, brackets, quotes, etc. These are to be cleaned. The second one is text normalization. This includes the conversion of items such as dates, time, numbers, currency, phone numbers, addresses, and abbreviations into normal orthographic form, that is, expansion into a phonetic representation. For example, abbreviations like MR dot, MRS dot, DR dot, special symbols like @ hash, $sign, percentage sign, etc. should be converted into its corresponding full form, that is, Dr. John had $5 should be converted to Dr. John had $5. However, such a conversion is not simple. For example, Dr. XYZ lives near Marine Drive is written, as you can see, Dr. dot XYZ lives near Marine Dr. dot. Now, how can you differentiate between these two Dr. dot? Dates and numbers should be handled properly. For example, rupees 1997 or year 1997. There may be some text normalization challenges depending on the language. For example, in English language, the texts are full of homographs, that is, words that are spelled the same, however, are pronounced differently. For example, read the book and the book was read, or the boy with a bow in his neck had to bow down to greet his relatives. You can see that the different words with different meanings are pronounced different, but the spellings are same. This must be taken care of. Now we move on to the next step after text processing, which is text optimization. The goal of text optimization is to cover a large number of syllables from less text material. There can be various ways of text optimization. The text optimization procedure may also depend on the speech sound unit used to build the TTS system. For TTS systems built with syllable-like units, the main criteria would be to include the maximum possible syllables in that language, and likewise for phoneme-based systems. An example of such a coverage, syllables in Gujarati language, is shown afterwards. The processing is done for each line in the text corpus. As in this figure, you can see the line consists of words ranging up to 10 to 20 words. Here, for each line, a score is calculated. This score would be based upon the number of new syllables, which are syllable that has not already been selected in the line, and the frequency of the syllables. After each of the iteration, top 300 lines were appended to a file which would contain the optimized text. The speech data is then recorded such that at least 95% of the syllables are covered. Although optimal text selection is good for reducing the size of the corpus, voice talents found it difficult to switch from one topic to another. It should be ensured that the topic across a paragraph was not changed during the recording to maintain the flow while recording. Now we move on to the next step, text to phoneme conversion. It is the conversion of the string into the basic speech sound units selected for a particular language. Speech synthesis systems use two basic approaches to determine the pronunciation of a word based on its spelling, a process which is often called text to phoneme or grapheme to phoneme conversion. As phoneme is the term used by the linguistics to describe distinctive sounds in a language. So there are two approaches to do this. The first one is dictionary-based approach and the second one is rule-based approach. The LTS rules are language dependent. An example of these rules for Hindi language is shown in many research papers. Now we move on to the next step, which is recording of speech data. The primary task after the text selection is a recording of this speech data. This is the most time-consuming task in the process of building TTS voices for a particular language. Several measures have to be taken to ensure that the recording procedure is done properly to build a sound TTS system. The important procedure in recording of speech data is the process of speaker selection and careful recording of the speech data in a good recording environment. The first task is to select a speaker. To record the speech database, it is necessary to select a good voice talent. The process of choosing a voice talent is not an easy task. The speaker should mostly be a professional voice talent who can speak with the same tempo, pace, and has especially soothing voice to hear. For example, newsreaders, radio jockeys are preferred for this task. So, the two approaches for doing this. In the first approach is to collect speech samples from various voice artists who are native speakers. For example, 10 males and 10 females. Sufficient amount of data can be collected from the possible potential candidates such that a primitive TTS system can be built. The candidate with the best quality of TTS system can be chosen as the speaker for recording the entire recording. The evaluation of the quality of the different TTS can be done through listening tests, which may include evaluating the naturalness, pace, pleasantness, the voice ability to mask concatenation error, etc. In the second approach, the speaker is selected based on to pass the recorded speech through signal processing modifications like pitch variations, which is done from minus 15% to plus 15%, tempo variations from 50% to minus 50% through standard signal processing toolkits. The speech files which these variations can be saved and the modified files can be directly given to evaluate for quality. The speaker whose voice sounds good even after these modifications can be selected as the best speaker for a TTS voice. Now, after selecting a speaker, we move on to speech data recording. Utmost care should be taken while recording the speech data. There are chances that there may be several errors during the recording of speech data. The following issues should be taken care of during recording of speech data for the voice-over artists. And those are appropriate recording room, transcription errors, pronunciation errors, speech recording duration, and recording content. The recording is generally recorded at 48 kHz sampling frequency and then downsampled to 16 kHz depending on the requirements of the platform of system building. Like unit selection speech synthesis by festival framework requires speech at 16 kHz. Now, the second portion of this module, which is the labeling of speech data at appropriate speech sound unit level, is to be discussed. In this unit, we'll discuss two kinds of labeling methods. The first one is phoneme based labeling, while the second one is, as you can see, syllable based labeling. So in phoneme based labeling, we'll be describing some algorithms, some techniques and some steps in this kind of approach. So next to text collection and speech data recording, it is needed that the speech data be labeled at the appropriate speech sound unit level, that is corresponding to a particular sound unit, say phone or syllable, etc., and equivalent text label are assigned to it. However, there is a lot of inconsistency involved with labeling of speech data, that is, a transcriber will not transcribe an utterance similarly at different instances. In addition, as the duration of the speech sound unit is decreased, that is, at the smallest phoneme level of labeling, the difficulty in transcribing and noting the exact boundary for the sound units becomes a difficult task. The segmentation can be at the phoneme or diphone level for languages like English, syllable level for Indian languages. Few of the possible approaches are going to be discussed in the following sections. So in case of phoneme based labeling, what we do is, in particular, there is no need for large amount of reliable segmented speech data, for instance, for improving speech recognition and synthesis performance. To segment the speech signal at appropriate sound units of speech, there are mainly two approaches, namely manual versus automatic segmentation algorithm. Then manual segmentation is time-consuming and tedious process, even though manual labeling may have long-term impact. No two human annotators can identify the phonetic boundaries exactly the same. This may be due to the cognitive factors such as reflex, attention, vocabulary, lexicon, etc. Now, out of the 9 different kind of approaches and methods and steps, the first one is phonetic segmentation algorithm. For automatic phonetic segmentation, various approaches such as supervised and unsupervised methods are proposed. Supervised methods require extensive training on speech material. The training material needs to be transcribed in terms of the speech sound units determined by the suitable segmentation algorithm. On the other hand, unsupervised methods such as maximum margin clustering, jump function, group delay do not require such training. In addition, unsupervised methods are based on human knowledge and understanding of the nature of speech and are therefore language and speech style independent. These methods simply use appropriate signal processing algorithms followed by the picking algorithm to detect the acoustic phonetic boundaries. So, in case of unsupervised STM-based phonetic segmentation, the human perception system responds to transitional stimuli more dominantly than stationary stimuli. This information is exploited in STM approach. What you can see here is a spectral variation which is very useful to detect phone boundaries. In A, you can see a time domain speech signal. B corresponds to phoneme label, while in C, you can see the corresponding phoneme label for an utterance, which is taken from Gujarati database. The spectral features used for speech segmentation is MFCC. The speech signal is transformed into frames which is computed over 30 milliseconds Hamming window. and then transformed into a set of 10 DMFCC, excluding the zero order coefficient that represent the total signal energy. The frame rate employed in this study was 100 per second, that is 10 microseconds frame step or frame increment. After computing MFCC, they used STM to capture the spectral transition between two phones. The STM employed in this study was the same as that of proposed in the earlier study. This STM at frame I can be computed as a mean squared error. The formula for which is, you can see here, Ci, which is the STM at given frame, is equals to summation over L equals to 1 to L, AL square over I whole divided by D, where D is the dimension of the spectral feature vector, which is 10 in this case, and AL is the regression coefficient or rate of change of the spectral feature defined as below. As you can see in this formula, the ALI is equals to summation over j equals to minus I to I MFCCL of j plus I multiplied by j, and then the whole multiplied by the summation over j equals to minus I to I j square. Now here j represents the frame index and I represents the number of frames on each side of the current frame used to compute these regression coefficients. It is evident from this equation that STM inherently embeds the delta substrum calculations. It is also possible to use other spectral features of speech apart from MFCC in STM. For example, Kochlier filter substral coefficients, which was recently developed by Q Li and Yan Huang, primarily for speaker recognition task. Now we'll move on to another kind of the approach, which is perceptual linear prediction substral coefficients. So perceptual linear prediction is one of the LP-based analysis methods which incorporate a nonlinear frequency scale and other known properties from the psychophysics of hearing. In PLP, Fourier transform is applied to compute the short-term power spectrum, and the perceptual properties are applied while the signal is represented in filter bank. The spectrum is transformed to a Bach scale, and this spectrum is pre-emphasized by a function which approximates the sensitivity of human hearing at different frequencies. The output is compressed to approximate the nonlinear relationship between the intensity of a sound and its perceived loudness. The all-pole model of LP is then used to give a smooth, compact approximation to the simulated auditory spectrum. And finally, the LP parameters are transformed using recursive relations to substral coefficients for use as segmentation features. PLP analysis is more consistent than conventional LP analysis with human hearing. As you can see in this block diagram for computation of PLPCC, you can see a speech signal goes into pre-processing, then a critical band analysis is being performed, then equal loudness pre-emphasis is done, and then it is converted into LPC, and then the substrum coefficient computation using recursive relation is being performed to derive it into PLPCC. So these are the steps that are followed before entering to the stage of PLPCC. Now the labeling of STM based boundaries has been done. The segmented boundaries are obtained at phone level using STM algorithm. The issue is to use these segmented boundaries effectively in TTS system development. For that purpose, text material for a particular language can be used. This text material is converted into phoneme sequence. These phones are aligned with automatically estimated boundaries. In this step, the phone or syllable boundaries are estimated automatically. The block diagram for generating the segmented labeled file is shown, which you can see. So firstly, to align the estimated boundaries with exact number of text, the steps are followed. Firstly, check whether the number of estimated boundaries from phonetic segmentation algorithm is equal to the number of ground truth boundaries from text material. Then, if not, then check whether it is less, and if found, then go to step 3, or in case it is more, go to step 6. Thirdly, if it is less, that is, if it is less than NP, then insert Ni equals to NP minus Ni, number of boundaries. For that reason, difference between estimated boundaries is taken, and where the difference is larger, the boundaries are inserted. However, the length of that particular segment will depend upon duration of previous level. Step number 5 is to repeat step 3, step 4 and step 5 until Ni is 0. If it is more, that is, if Ni is greater than Np, then remove Nr, which is equals to Ni minus Np, which is number of boundaries. In that case, we merge minimum duration segment to its right or left segment. Then again repeat step 6 and 7 until Nr is 0. Next we move on to supervised vertebrae-based phonetic segmentation. Supervised vertebrae-based phonetic segmentation. In this segmentation algorithm, an alignment algorithm is used for phonetic segmentation. The process of computing the vertebrae path over training data is called forced alignment. Here we do not know the optimal state sequence assigned to each observation sequence. There are a few major steps that were carried out to generate phoneme-based label files. First one, preparing 5 minutes of manual data at phoneme level. HMM was trained using MFCC features corresponding to each phoneme class. Remaining WAV files were labeled using a speech recognition system with the help of HMM. Now again HMM was trained using entire speech data. Lastly, the step 3 in step 4 was repeated until convergence is achieved. Next we move on to relative performance of various segmentation algorithms. As you can see in this table, the algorithms and their corresponding accuracy is being shown. In order to evaluate the relative performance of various segmentation algorithms, 10 minutes of manual phoneme label Gujarati speech data was taken. If detected boundary of phoneme is within 10 microseconds duration, which is known as tolerance interval of the manual boundary, then it is considered as correct. Next, we will move on to the effect of phonetic segmentation on speech quality. In order to evaluate various automatic phonetic segmentation algorithms, we require manual accurate phoneme level speech database, which is not available for Gujarati language. Now question is how to measure accuracy of various automatic phonetic segmentation algorithms. Hence, it was decided to build real-world applications such as TTS to evaluate the performance of automatic phonetic segmentation algorithms. Hence, HMM-based speech synthesis system has been built on Gujarati speech database in order to measure relative performance of various segmentation algorithms. Now, a subjective evaluation is done. 5 synthesized utterances from held out database from each HTS system was taken and mean opinion score analysis and degraded MOS from 20 Gujarati native subjects. Files from different subsystems are played randomly and subjects were asked to give a score in 1 to 10. Then from these scores, MOS and DMOS are calculated for each system. Here, MOS represents mean opinion score and DMOS represents degraded mean opinion score. Now, WER is calculated using this formula, which is I plus D plus S by T, where I is the total number of insertion, D is the total number of deletion, and S is the total number of substitution. Now, the table itself represents the MOS, DMOS and WER analysis of developed HTS. For different algorithms, you can see the data. Now, we'll move on to objective evaluation. Widely used perceptual distance measure is used for measuring the accuracy of the spectral envelope of the synthetic speech with respect to natural speech. We have used dynamic time warping, which is DTW based approach to align natural speech and synthetic speech, as both have different durations. Normalized DTW based perceptual distance is given by MCD equals to distance calculated from DTW divided by number of points during backtraced, where number of points during backtracked tracing in DTW is used as normalizing factor for distance calculated in the data. The table shows the evidence that in case of female voice, vertivi based approach and STM with PLPCC based system gives less MCD score. In case of male voice, all methods of labeling have almost similar results. However, STM with MFCC, PLPCC and vertivi based method has slightly less MCD score than other methods. Now we'll move on to another approach of the labeling, which is syllable-based labeling. Syllable-based labeling is mostly useful for Indian languages, as Indian languages are known to be syllable-based. Low-resource languages such as Indian languages hardly have any vocabulary-independent continuous speech recognition systems that are readily available to perform transcription. There are different approaches in this kind of labeling, which we will discuss as below. Group delay based labeling or DON label tool, which is developed by IIT Madras. A syllable typically consists of a high energy vowel surrounded by low energy constants. Thus, the syllable boundary can be considered a point where the energy reduces and increases again when the next syllable approaches. Therefore, high energy regions in the short-term energy contour correspond to a syllable nucleus, and the valleys at both ends approximately correspond to the syllable boundaries. For speech synthesis, the boundaries must be accurate and consistent. To assist this, a separate kind of experiment is being done, and a semi-automatic tool was developed based on group delay functions. As in the figure, you can see the DON label leveling tool for a Hindi utterance, Holi Rangoka Prabhav, which you can see here. The leveling tool of Hindi represents MESPA, EHMM panel, still air panel, wave panel, text panel, GD panel and VOP panel. Similarly, in the next figure, you can see the DON label leveling tool for a Gujarati utterance. Now you can see the stark difference from the two kind of languages labeling. The percentage of correctness of the tool is used as a measure to check accuracy. The POC is calculated as per the formula which you can see. Now we'll move on to Gaussian filter-based segmentation. With the objective of removing the local variations in STE contour of a speech signal while retaining the syllabic structure, the Gaussian-based segmentation approach has been attempted. It has been observed that if the short-term energy contour of a speech signal is low-pass filtered with the Gaussian filter, Then minimas of the filtered signal correspond to syllable boundaries. To compute the syllable boundaries, following steps are followed. For a given speech signal, compute its corresponding STE sequence using overlapped window. Low pass filter the STE sequence using Gaussian filter to set filtered STE sequence. Locations of the minimas in the Gaussian filtered STE sequence gives estimated boundaries of syllable-like segments. Another approach is a spectral transition measure-based segmentation, where we will describe spectral features, segmentation algorithm using STM approach, which will summarize the STM-based segmentation. The spectral variation is very useful to detect syllable boundaries. In addition, most neurons in auditory cortex have been found to respond poorly to steady-state stimuli and better for transitional stimuli, indicating key motivation for using STM to detect syllable boundaries. Segmentation algorithm, which is done using STM approach. So there are 3 steps followed in this approach. Firstly, transforming the speech signal into frames at segment level. Then transform a speech frame into a set of 10-dimensional MFCC, excluding the zero-order coefficient that represents the total signal energy. Finally, computing STM after computing MFCC. The formula used to do this are shown, which you can see. Now, the percentage of correctness of different segmentation method for Gujarati language is being shown in this table, where a segmentation method is described and the corresponding percentage of correctness for female voice and male voice is given. Now, the correlation of segmentation with TTS quality is being performed. The labeling for speech signal segmentation is directly linked with the quality of the TTS system. To study the effect of segmentation on the TTS quality, the approach described lastly is used here. 6 different Gujarati TTS systems were built, 3 each for female and male voice, corresponding to 3 different segmentation methods. That is, Don label tool, which uses minimum phase group delay-based segmentation algorithm, Gaussian-based segmentation algorithm, and STM-based segmentation algorithm. The TTS is built using Gujarati database of 38-minute, consisting of 184 utterances as speech corpus covering 5,350 syllables. The table, which you can see, denotes the intelligibility evaluation of different TTS system. In percent, you can see the correct word synthesized with extra component at front, correct word synthesized with extra component at back, correct word synthesized with extra component at both front and back, partially correct word synthesized, wrong word synthesized. Now the group delay based, STM based and Gaussian based, 3 kind of approaches are shown and their corresponding male and female voice percentages are shown. So the quality of TTS system depends on the accuracy of segment algorithm. In this module, we have discussed the text collection, selection of speaker, and the appropriate methods which are used for speech data labeling are discussed. The most tedious part is the labeling step. Now, in this module, we have discussed the various methods of speech labeling. So, the 2 approaches, the one is done at the phone level and the another one is done at the syllable level. At the phone level, we have discussed the hidden Markov model based TTS approach, and at the syllable level, we have discussed the unit based selection techniques. Now, after the labeling, for the evaluation purpose, we have shown that the segmentation accuracy affects the TTS quality. In the next modules, we will see in detail the labeling methods, the synthesis approaches for concatenative synthesis approach and statistical parametric synthesis. Thank you.